Okay, here's my first attempt at our online recording. We covered a bit of this stuff in class, so I'm just going to very quickly note for the PDFs, if you want to go online, that there is this review section that goes through all of the basic components of the Earth, how the Earth system works, etc. If you don't feel confident in that stuff, do make sure you go back and do it because all of earthquakes and all of volcanoes are going to absolutely intimately be relying on this stuff. It's fundamental to the course. So do go back and make sure you understand all of these aspects in terms of how plate tectonics work. Okay, so where did we get up to in class? In class, we basically got up to watching this video right here that showed the aftermath, or rather the effects, the impacts um, of the Tangshan earthquake of 1976. So this is probably the most infamous earthquake in history, also arguably the deadliest earthquake in history. Let me just get my little laser pointer here. Where's my little laser pointer? So the numbers are highly disputed. The official government numbers are around 300,000. Other estimates put it upwards around 650, 700,000. Again, as I noted at the beginning of class, you see a lot of difference between estimates that academics come up with and the numbers that come out from the government. Sometimes governments want to downplay because of fear of embarrassment the number of people who die. You're going to see this later on in Burma, for example. Other times, governments have a tendency to inflate the numbers to inflate the need for aid because countries are less or more likely to act if the magnitude hits an astronomical amount. Anyways, in this case, it's more of an embarrassment kind of thing. This is the numbers coming out of what at that point was a very closed communist government. We've just come out of the Cultural Revolution at this point, which, if you guys want to look into Chinese history, is a fascinating and terrifying time in world history. So this is absolutely a monumental event. And I note here that the entirety of this thing lasted 23 seconds. So in terms of shaking, you can get earthquakes a lot longer than this. But the impact, as you can see in this photograph here, was devastating. This is a large city, and you can see there is nothing left. There's a building here, a building here, but almost the entire city was reduced to rubble. So this is a magnitude 7.5, and we're going to talk about what that means in a moment. But it's a big earthquake. But again, this is not a world-shattering earthquake, right? It was world-shattering to the people, but this is really driving home the issue that a earthquake and the effects of an earthquake, and really of all of these natural hazards, is, remember, an impact or an intersection of the hazard itself as well as societal issues, susceptibility, exposure, etc. In this case, we have a relatively large population. The epicenter was quite close to the city, as well as a society that was really susceptible. Right? These buildings were not made to fall down. And there are other things you'll see in a second that really played a role in the devastating effects of this. So here are some shots again. This is pardon the low resolution here, but 47 square kilometers. So that's 10 kilometers by 4 kilometers. That's essentially all of downtown Sydney, over to the university. It's probably about 10K from downtown to the university, and then a 4K wide strip. Completely gone. Completely gone. You can move further outwards. 80% of dwellings destroyed for 370 square kilometers. It's a massive area. Now, note that we've moved from those M values, which had Arabic numerals associated with them, to these Roman numerals here at MMI. So I'm going to explain what that's all about in a second. You can keep on going out. 40% of dwellings destroyed by 1,800 square kilometers. And finally, as far as 33,000 square kilometers, you were still causing damage. So notice MMI over here. This is 7. That numbers mean 7. So this is an area which is 3 times the size of Cape Breton. There's some damage. So an area 3 times the size of Cape Breton, you could be in Antigonish and your house would have cracks, your windows might have imploded, etc. I mean, this is an absolutely devastating earthquake. So let's unpack those Roman numerals and the Arabic numerals, the M's and the MMIs. What do those mean? Well, they mean 2 very, very different things. There's 2 ways you can talk about the size of these things. The first thing we can do is we can talk about some measure of actual energy, right? Or we could try to talk about the force of the energy as realized on the ground. So what is the actual damage like? And what is the energy that underlie these? And these things are not going to be the same thing, right? These are not going to be the same thing at all for a number of reasons that we'll unpack in today's lecture and the next lecture. So these are two totally separate, different ways of talking about things. When you see MMI or you see M, very, very different things, right? Both useful and obviously related. So this is the amount of energy released. The amount of energy released is obviously going to impact the intensity or the damage which is caused, but they're not always the same thing. So how do we measure the first one there, the amount of energy released? Well, we don't. I mean, you cannot measure directly the amount of energy released because the energy is released at source, by which I mean it's somewhere deep underground. We have no instrument that's capable of doing that. Instead, what we do is we measure the amount of energy that appears on the surface, and we extrapolate from that, right? We make estimates based on that of how much energy was actually released at the source. So we measure that energy with a device called a seismograph, if it actually has a readout here, or a seismometer sometimes, if it's just a digital instrument. And those are recorded, or at least were traditionally recorded in one of these over here, which is a seismogram. So seismogram is the actual printout of this thing. And these devices are really simple. I mean, it really is, in its most simple iteration, it was essentially a pen on a spring, attached to, or hung from a spring with a roll of paper underneath it. And when the Earth moves, the spring compensates for that movement. Do I have an image on the next page? No, I have an image somewhere in here, but I'll just describe it right now. The spring compensates for that movement, so the pen doesn't actually move, but the ground is moving, and therefore the paper is moving. And so as the paper moves around underneath the stationary pen, the pen is stationary because that spring is absorbing all of that movement, it ends up making these lines you see here. Now, we don't really have physical readouts like this anymore. If you go, like the university I did my undergrad at, UBC, they had one running there, an old school one where you could watch it recording in real time. But most of it is, of course, digital now, but the principle is exactly the same, right? You have one recording device and a thing which is suspended on a spring, which is moving relative to that thing. And now we record it digitally. So there's your seismograph, there's your seismogram that you're producing. And these guys here represent the relative amount of surface movement. And that is directly proportionate. That's going to be directly proportionate to the amount of energy released as well as your distance from that energy, right? As well as your distance from that energy. The second thing is intensity. So intensity is a measurement of the strength of shaking at a given location. So if the origin of the earthquake was somewhere in the ground below that spot, the further you get away, obviously, the less you're going to experience the shaking. But as you can see by the shape of these things, right, you can see that these are not perfectly concentric circles. So there are other factors that come into play here as well. And we'll talk about those other factors actually next lecture, I think. These are influenced by many factors. We'll talk about these factors later on. So right now, I just want you to be familiar with the idea that you have a scale and that's represented with these Roman numeral numbers. And the larger the numbers, the more intense the on-the-ground effects are. So, a house with a crack in it versus a house that completely collapses. The ground moving slightly versus the ground completely rippling, right? Literally just moving like waves on the ocean, right? Those are possible impacts, possible manifestations of an earthquake. So that is intensity, and this is measured with these numbers right here. So the intensity scale, what are our first scales? Right? These are the very first, and they go all the ways back to this really famous earthquake in 1755 to some degree. So in 1755, there was a big earthquake in Lisbon. People who study classics or study English might have looked at this. This is referred to sometimes as the beginning of seismology. I'll unpack that in a second. This is a massive earthquake followed by massive fires, which you'll see are often some of the deadliest impacts actually of earthquakes, and then a tsunami. So it was the triple feature of the way that earthquakes kill. Earthquakes cause buildings to fall down. Earthquakes cause, candles to fall over as well. In this day, lamps to fall over, which would cause combustion. And then sometimes if you are in the right kind of geologic area, and we'll unpack this later on, and obviously proximate to an ocean or to a large body of water, a lake can do it too, you get a tsunami as well. And so the numbers are sketchy here, but at very least tens of thousands of people died, maybe up to 100,000 people. And this is particularly important because of the effect it had on the philosophy of people who are in the middle of the Enlightenment at this point. So if you want the general context, and this is where it comes up in your English classes, you may have read this writer here, Voltaire. He was a famous thinker and satirist from the 18th century. This book here is about this guy, this naive man who has this view that everything in creation is perfect. It was created by God in this perfect way. And therefore, regardless of how horrible something is, he always has these rose-colored glasses. And he sees everything as perfectly designed, part of this perfect functional thing. So this is a satirist at a time when people are starting to seriously think about how the world works and the relationship between the natural world and the theology that they had, inherited from the Middle Ages. And so there's a lot of conflict, intellectual conflict going on here. And what was particularly damning about this earthquake is it occurred on a Sunday when people were in churches, and the buildings that were impacted, as we know now, are based on the structural designs of the buildings, and so and nothing else. And so churches, a lot of these major churches fell down during Mass in a very Catholic country and killed thousands of people in churches. But as Voltaire and other people dryly noted, in some areas brothels did not fall down, and so you ask, what kind of God would do that? So this caused a bunch of turmoil. But this is not really important to us in this class. Is how does it affect the social structure and the political thought and all of those sorts of things, theology, philosophy. What we're interested in is the effect on the science, right? How do these scientific ideas evolve? So that takes us to this guy right here, Carvalho. Carvalho was kind of a general, and he was put in charge by the local royalty of dealing with the aftermath of this thing. And he did it really responsibly with a business-like attitude. So this is a famous quote. Maybe it's apocryphal. I don't know if he really actually said this, but this is considered to kind of sum up his attitude towards it. And asked, how do you deal with this? And he says, bury the dead, heal the living. So very practical. And what else can you do? You can mourn, you can cry, but you also got to get on with things, and you got to bury the dead, and you got to heal the people you can help. But what's important about him is that in the process of reconstruction, he did a couple of things. One is mandated that buildings in the future be built somewhere better. This is sort of the first iteration of a civil engineering code about earthquakes. Obviously, don't overstretch this. This is not manifesting in that. But they did do things like build models and play around with them a little bit to get an idea of how things might respond. But what is really important to our discussion here of measurements is that he sent out a questionnaire afterwards to people of various distances away and asked them, what did you actually experience? And that really is the first intensity survey, because that's all intensity is what happened on the ground. So traditionally, we would actually do it in exactly the same way. We would just phone people up or talk to people and ask, what did you experience? We'd also look at physical damage as well. And that's how we would make up these intensity maps. Now we actually do it through social media a lot, because if you just go on Twitter after an earthquake, immediately, hashtag earthquake, you're going to see this happened, this happened, this happened with, geotags associated sometimes, or people just, posting sometimes direct information, geographic information. But if not, you can extrapolate from where they say, the photographs, the locality, etc. And we can make a map there of what area is experiencing damage. Now that's really important if you want to both understand the fundamentals, as you'll see in a second, but even more important to get to this part, bury the dead and heal the living. If you want to know how to respond to an earthquake, it doesn't matter whether it was a magnitude 7 or 8 fundamentally. What you want to know is, where are the dead, where are the injured, and how do you get to them? So you want to know, if you are doing disaster response, you need something like an intensity scale. If you're interested in understanding earthquakes as a whole, you want to know more fundamentally about how energy is released in these systems. Right? So the intensity scale gets its modern incarnation through a guy named Mercalli. And this is a modified version. So when you see the MMI, it's modified Mercalli intensity scale. So we've taken it, we've modified it a little bit. You do not need to know everything in here. What I would like you to know is that 1 is essentially nothing at all happening, so felt by a few people under especially favorable conditions. So a 1 or even a 2 is kind of, you're hanging out and someone goes, hey, did you feel that? And you go, feel what? And they go, I felt like it shook a second ago. And you go, no, I didn't feel anything. That's a 1 or a 2, you know? A 3 is you can't tell if a big truck just drove by or not. A 12 is you're dead. Right? Damage total, waves seen on ground surfaces. And that's a real thing. I'll actually show you some YouTube video of the ground literally behaving in a wave-like manner. It's really totally crazy to see. Lines of sight and level distorted. That's because the ground is suddenly moving in waves. Objects literally thrown up into the air. So 12 is extraordinarily bad. That's the top of the scale. 1 and 2, you're not feeling, or you may feel if you are in exactly the right circumstances to feel it. If you're going for a run or something, you're not going to feel this. So this is the Mercalli scale. And here is your ranking over here. Okay, again, do not memorize this, but there it is. That's directly out of your text. I'm actually not sure. I made this a while ago, so this may not correspond exactly to the table in your textbook, but just look it up in the index. You'll see exactly where it is. All right, so if you look at the Tangshan earthquake of 1976, here are Mercalli values. They're not numerical values here. They're color-coded, which is usually how this is shown. But you can imagine that this effect here is, you know, a 12 or 10 or something. Or sorry, over here. And this would be, I don't know, this is a 7 or something. I mean, this is, you know, serious damage. Those are not real numbers. I'm making these up. And you can see that there is overall, as you might expect, a decrease in damage as you move away. But you can also see that this thing is not a circle. It's not a bullseye, right? It's this weird oblong shape with weird pockets that defy. Why is this area here experiencing less damage than everything around it? This one here experiencing more, even though it's that far away from all the other orange areas. So we'll unpack that later on. But right now I just want you to concentrate on this basic idea that the further away you get, all other things being equal, the less the damage is going to be. Okay. So here, there, by the way, this is an old school seismograph. So this is your spring. So when the ground moves, it's moving back and forth like this or rippling like this. This whole thing is going to move. This whole thing is going to move. If you're standing on it, you're going to move. This pin with the weight is not going to move. And that's because as this moves back and forth, the spring is going to absorb that motion. So this is, you know, relative to its original position, going to be stationary. Relative to this, it's moving because this is moving. But that is actually going to stay totally still because this spring over here is grabbing all of that motion. A little bit of physics to wrap your head around, but it's true. All right, so the magnitude scale is most commonly associated with this guy here, Richter, who was a California seismologist, proposed this scale in 1935. We don't actually use truly the Richter scale. It's slightly mathematically different. They're functionally equivalent at almost every level. But the Richter mathematics were a little bit, they were based on California earthquakes, so they didn't quite capture the totality of sorts of earthquakes. And this is an estimate, remember, of the total amount of energy released, right here, estimate of the amount of energy released. And the most important part to realize about this scale, it is logarithmic. So this is a weird thing if you're not used to thinking about scales like this. This is a weird thing to wrap your head around. And it's one of the biggest misconceptions we kind of have. When we look at something which is, you know, a 5 versus a 7, you go, oh, that's only 2 bigger. Or a 7 versus a 9, you go, oh, that went up 2 more. But at each scale, you're going up, as you're going to see in a second, by a multitude or by a multiple of what came before. And so things get really big, really fast. All right, so right now we use a thing called the moment magnitude scale, or you just see sometimes it's just M is how it's represented, and that's essentially the Richter scale. It's just a slightly modified version. Okay, so how do we calculate this? Well, again, we don't calculate it. We make estimates of it. We measure on the surface the ground movement, and we use that to make an extrapolation based on our understanding of the distance away that the seismograph was from the actual source of the earthquake, which is somewhere deep underground. We use that to estimate this energy or moment. The actual measure of energy, how much energy is released by an earthquake, is a function of 3 different things. First, the fault area. So that's the total area which is actually doing the moving. The second part is how far did that total amount of rock move? And the third is the properties of the rocks themselves. Not every rock is going to generate the same amount of energy. So we'll unpack that later on. But this is how the actual energy of the earthquake is determined by these three things. How much area moved, how far did that area move, what were the rocks like that were doing the moving. So this is what we are trying to estimate. We're estimating it by the impacts felt on the surface, not the damage, but the actual movement on the surface recorded by this. So we extrapolate this, we estimate this from measurements on the surface using, some modern version of that. All right, so a logarithmic scale. What I mean by that is it is kind of an exponential scale and is moving up by a factor of 10 at every point in terms of shaking on the ground. It's actually by an even larger factor in terms of actual energy related. And this is not to scale because at this point, if we're moving up, that's going from, this is going from 10 to 100, right? But this is going to be 100, 1,000, 10,000, 100,000. So the difference between here, this one is between 10 and 100. That's 90 points difference. But by the time you get here, 10, 100, 1,000, 10,000, 100,000, a million. This is 900,000 points different, right? So these are radically different jumps. So if this was to scale, this would shoot somewhere way outside of the room you are in, up into the sky somewhere. This is pulled down here, right, to make it so that you can visualize this. And this is why we use these scales, is because the magnitude, the actual amount of energy released is so variable with these things, going from astronomically large in terms of these big 8, 9 earthquakes down to, still crazy on a human scale, but much more manageable amounts of energy. So we need a mathematical way of representing it that captures that gigantic range of values. And so we do it in this way here, using this logarithmic scale. So here's an attempt to help you kind of try to visualize this. And I don't know if these are actually useful or not. How much energy does the US use? Well, this is a crazy amount, but you may not think about that. Also, volcanoes erupting. Again, it's really hard for people to visualize how much volcanoes release in terms of energy. So I don't know that these are actually useful analogs up here, analogies. But if we go down here, so this is a really large, this is not Hiroshima, right? This is a really large test. I think this is a hydrogen bomb. You can Google that. This is a big nuclear explosion that the U.S. government tested, and that's coming down here, right? And at this point, we are coming down quite low in the intensity relative to these earthquakes coming up here. But the time we get up to, a magnitude 8 and there are 9, and there have been very few magnitude 9s that we've ever measured, at that point you're, getting into the entirety of all the energy used by all of the U.S. in a year, which is an astronomical amount of energy. By the way, if we're thinking about climate change, which we'll discuss later on, think about one of the most powerful things that literally happens on Earth. We use that amount of energy in the U.S. either way. So you can actually flip it around the other way and go, holy crap, we use a lot of energy. Or you can go, holy crap, that's a big earthquake. Either way. If you click on this link, it'll take you to some other ways of thinking about this. All right. So that 10 times factor is the amount of ground motion change. But you need more energy actually released at source to cause that ground motion change. So when you think about the actual energy release, it's even bigger. It goes up by a factor of 32, which means that the difference between 1 and 3 is 1,000-fold. Right, 1,000-fold. We're jumping up insanely fast. Now, the math gets a little bit complicated, and not complicated, just unintuitive when you start breaking it down into smaller intervals. So I'm really not going to make you do this. I might ask you a multiple choice question. These are approximations, but if you want to think about it, every time you jump up 0.1, you are jumping up 1.3 times. So the difference between a 5 and a 5.2 is 1.3 times 1.3. Right? So the difference between, so by the time you get up a 5 and a 5.3, a 5.3 is twice as strong in terms of ground shaking, and about 3 times as strong in terms of energy released as a 5. So it really dramatically ranks up. A 5, 5.3, those don't really seem like very different things, but they are dramatically different events. They are dramatically different events. If you have a headache, which is, X bad, or twice as bad as that, that is a big deal. If you get a raise of twice your salary or 3 times your salary, that is a huge amount. But that's the difference between 7 and 7.3. So let's look at this in practice. Here is the big earthquake in Japan that caused damage to the Fukushima reactor, and here's the one in Haiti. So this one killed a bunch of people, but actually really through the tsunami afterwards. The earthquake itself did not kill that many people. And here's the one in Haiti where we killed at least tens and possibly up to 250,000 people. This is a 7 versus a 9. How much bigger is this one than this one in terms of actual magnitude, energy released on the ground movement, as opposed to actual damage, which is intensity over here? Obviously, this one caused more damage, right? But which one of these ones actually released more energy? Well, you've got a 7 and a 9, so you remember that in terms of amplitude, that's on the ground motion. This is going to be 10 times 10. So an 8 would be just 10. Jumping up to a 9 does another 10. So 10 times 10 is 100. Energy is going to be roughly 33 times 33, which is going to be roughly 1,000. It's actually in between 32 and 33. So if you want to start doing things like a 3.6 versus an 8.6 or a 3.2, this is, by the way, one that happened in 2015 off of Nova Scotia. So we do get earthquakes in Nova Scotia. That's a 3.6. In Indonesia, there's one 5 times bigger. So how do we get to that? Well, remember, it's going to be 5 times 5 times 5, 10 times 10 times 10 times 10 times 10 in terms of amplitude. And this is going to be about 33 times 33 times 33 times 33 times 33, which is going to give you that number right there. You can calculate it if you want, but I'm going to invite you, instead of using paper, to go and just click on this link or just follow up this thing here, and it's going to take you to a calculator where you can put whatever number you want in, and it'll give you differences. You can play around with that. So a reminder that every time you jump up one of these decimal points, there is actually a dramatic increase in energy that we really need to remember, especially when you're comparing things like aftershocks. Okay, so here is a 5.2. It was an aftershock, and it was after a 5.9 magnitude earthquake. This is 2018. I put this in last year in class. This is in Haiti. Just a reminder that Haiti remains seismically active. So how much bigger was the original earthquake than this 5.2 aftershock? I mean, this is only 0.7. These are roughly the same size, right? Well, they're not. You know that now. But if you look at it on the face of it, that aftershock seems almost as big. But of course, the original one was 5 times as large in terms of on-the-ground shaking, right, amplitude, and it released 10 times or 11 times the amount of energy. So this guy here, the first one, was 11 times the size in terms of initial energy released. Okay, so great. That's how we measure, how we quantify these things, how big these things are. What causes earthquakes? Well, plate tectonics. I told you that. Plate tectonics causes earthquakes. Sure. But let's unpack that. How does plate tectonics cause earthquakes? Well, it must be something to do with the movements of the plates. I've showed you these maps, and I've showed you that at every kind of plate boundary, you see earthquakes. You see them where the Earth spreads apart, which remember is a divergent boundary. You see them where the Earth moves together, which remember is a convergent boundary. Those are subduction zones where a plate goes down, or where two continental plates hit each other and nothing can subduct. That is a continent-continent convergent boundary. But you also see them where plates slide past each other. And you see those at transform faults, right, or strike-slip faults, transform boundaries. You can in fact see them at other areas as well that are completely removed from plate boundaries. But the vast majority of these things we find at plate boundaries. So that's ultimately what's powering these things. But how directly does plate tectonics make an earthquake? So that's what we're going to be talking about now. So if you go back in history, any locality, any place where human beings have experienced earthquakes, they have struggled to come up with a way of explaining it. And you can click on some of these links. It'll take you to some of them. This is an early Japanese idea that there's a giant catfish under the ground that shakes its tail. Now, I don't know if the people actually believed this. Literally there's a giant. A lot of times people explain things in poetic ways, right? They use kind of allegories to explain things that they can't really understand, but they don't really think that there is a giant catfish. Within Japan as well and China, there was a deep kind of influence from the Chinese Confucian tradition, the idea of the balance of yins and yangs. And so there's also a lot of belief that earthquakes represented the manifestation of a fundamental universe kind of out of alignment, of a problem with yin and yang. And so you can So, for example, when an emperor was sick or was going to die, emperors are really strong in one of those. I forget if it's yin or yang. And so, if an emperor is getting ready to die, that would throw the entire world balance out of whack, and you could have giant earthquakes afterwards. I already noted that in one particular earthquake in early 20th century Japan, the balance balance going out of whack was blamed on foreigners kind of polluting the culture, and there was a absolutely horrific backlash, a violent backlash against Korean immigrants in the community. So, I mean, these explanations to try to explain these things through kind of supernatural effect, they can have positive and negative effects, but what they represent in all cases is some attempt to provide order onto the universe when the Earth that we know is a stable substrate. It's supposed to just sit there. I mean, literally, you get onto stable ground. You imagine the person on the ocean voyage, the first thing they do when they get to shore is they jump off and they kiss the ground and they're back on stable ground, right? They've got their land legs under them again. Well, sometimes the Earth just starts rolling around like the ocean, and that is terrifying. Sometimes a house, a home, which is a walled fortress, a castle, the strongest things we can have that assault all human assaults and weather, they withstand that. Those become instruments of death because they fall down on you. That throws the entire, our understanding of what safety is out of whack. The literal firmament we stand upon stops being firm. Literally turns to liquid, as you're going to see next lecture. Literally liquefies in some sense. So that's terrifying, and people need an attempt to explain it. And so if you look at the mythology, again, of any culture that's done it, you see these things. If you go to the Haida, right, there is a kind of mythological understanding of the earthquakes we get along the west coast with the Juan de Fuca plate, along the subduction zone there, up further north, the Pacific plate interacting with the North American plate directly. And so there, you get these sorts of things, whales and thunderbirds fighting. And did the Haida literally believe that was the case? I have no idea. But it was a way of understanding how these things work. And that's really what we had for quite a long time, was just an attempt to explain through metaphor, allegory, mythology, stories. And you find these everywhere. Again, you go to the Philippines, turtles, frogs, Loki, Zeus, all of these different attempts to explain these. And if you click on this link, it'll take you to some of these different things. So the first kind of attempt to explain these things in terms of a timeline. This is not to say that people in Japan or the Haida didn't speculate in terms of Earth histories that didn't evolve these kind of mythological explanations. But in terms of drawing a timeline from modern seismology directly back, in terms of what ideas influenced what ideas, it kind of traces through the Greeks, through European Enlightenment, as you're going to see in a second, jumps to Japan, and then comes over to California. So if you go back to the Greeks, you get sort of ideas that sort of make sense. So here are a few different people talking about Aristotle. The earth is essentially dry, but rain fills it with moisture. Then the sun, its own fire, warm it and give rise to a quantity of wind. So here maybe it's steam powered, right? Maybe it's steam powered. And these guys, remember, are living in very seismically active areas, but also because subduction zones are associated with volcanoes and earthquakes, they're seeing steam come out of the ground in that as well. So this is not a crazy idea, and it is one that's naturalistic. It involves quantities of gas expanding and putting pressure and things, but it's not remotely correct. Here is the 1600s, beginning of kind of the Enlightenment, and maybe these are explosions. Maybe that's what's going on. It's sort of the same idea, just different source, right? But there's something underground, and there's some kind of force within there. Robert Hooke, most famous for coining the term cell. He was a really early biologist, British, right? Yeah, he, again, thought that maybe it was explosions. So we're not getting a lot bigger or better by the time we get into the Enlightenment. We actually don't get a lot better until the 20th century, as you're going to see in a second. Again, more explosions, etc., right? After this Lisbon earthquake, you start to hear some ideas that start to make a little bit of sense. And obviously, you can see these are still into the 1800s. These are not, it doesn't catch on. But this is the closest iteration of our understanding as you might see. And what's interesting about this, and again, I said that this event takes you back to the origin of modern seismology. Is the idea that these events represent wave-like movements. So suppose a large cloth or carpet spread upon a floor be raised at one edge and then suddenly brought down to the floor. The air under it, being by this means propelled, will pass along until it escapes the opposite side, raising the cloth in a wave as it goes along. That's not, again, remotely the actual mechanism. It has nothing to do with movements of air underground, as you'll see in a second. But the idea that the energy transmits in a wave does capture something that you would really see on the ground if the earthquake is large enough, which is that the ground can move in wave-like manners. But it is fundamentally true about how this process actually works. The energy is in the form of a series of different kinds of waves that move through the ground with particles bouncing against each other in different ways that we'll unpack next class. So the real beginning of a scientific understanding starts really in Japan. So here is a fault. I'll unpack what a fault is in a second, but this is the first iteration of a direct relationship between movement along a fault and earthquakes radiating energy outwards. And you can read this here. The sudden elevations, depressions, and lateral shiftings of large tracts of country take place at the time of destructive earthquakes are usually considered to be the effects rather than the cause of subterranean commotion. But in my opinion, it can be confidently asserted that the sudden formation of the Great Fault of Neo here, right, was the actual cause. So people noticed, obviously, displacement, right, that the ground moves up or down or left or right relative to these faults. But people thought those were consequences of, say, underground movements of material. So this is the first iteration that it may be the actual movement itself which is generating that energy, and that the energy is a consequence of that movement, right? The energy you feel over here is a consequence of this movement right here. So this is thoughts coming out late 1800s in Japan, moving into the early 1900s. These two guys in particular, but I mean a lot of scholars underneath them. This school of thought in Japan is really where we start getting these ideas and attempts to start measuring these things. So John Milne in particular, John Milne was a British geologist who accepted an invitation to take on a role teaching in Japan and actually became the first academic seismologist in the world. So someone who was specifically appointed as a seismologist. And then he was subsequently, he went back after a couple of decades in Japan, continued his research, working with his Japanese colleagues to establish the first global network of seismographs, which showed that these things actually were global in extent in terms of how the waves affect, etc. So Omari was the man who took over afterwards with him, but all the time Milne's there, he's working with a research unit, right, of Japanese scholars. So it's this guy, essentially a British guy, and then a large unit of Japanese researchers who really start laying the ground, looking at the relationships between, shocks and aftershocks, between fault movements, gathering historical data on movements, all of the kinds of things that we associate with modern seismology. But we still didn't have, we had a better understanding of kind of the impacts, the extent, right, how energy releases itself in time and in space. But the source of the energy is still not understood at this point. So it's not until after 1906, with the famous and devastating 1906 San Francisco earthquake, that we actually get the mechanism proposed that we now understand to underlie the cause of earthquakes. And it's a really simple mechanism. Notice, by the way, all of this fire over here. So the 1906 earthquake essentially destroyed San Francisco. But the vast majority of the damage, I mean, you can see this is direct earthquake damage right here, but this is direct earthquake damage right here, but the vast majority of the damage was actually related to fires that started afterwards, gas lines breaking, and fires ravaging, both because fires started, but also all the water mains break. And this is a impact that happens even today in earthquakes all the time, is that not only do you start fires, but you lose the capacity to fight the fires because the entire infrastructure breaks. So this is a serious issue. Okay, so elastic rebound. This is what the explanation we come up with is. So what's elastic rebound? We'll unpack that. Just quick digression. Here's Omari again. World's greatest seismologist says San Francisco is safe. This is after. This is in terms of safety after the aftershock. So this is from a newspaper, San Francisco newspaper. So the Japanese government actually sent over a group of their absolute best seismologists to help with the investigation and also to study this event itself, because obviously the more data you get, the better you are able to predict and prevent earthquakes. And Omari was actually quite famous for having not predicted, but have forecast a particular earthquake, a particular city being at risk, and people didn't listen to him at the time. And it ended up destroying the city. Anyways, that's a digression. But what I wanted to note to you, just as a reminder of how horrible human beings can be. So Omari and his team of colleagues, Japanese colleagues, who came over again, sailed across the ocean on steamships, to help understand this event, were assaulted multiple times on the streets by anti-Japanese racists. I mean, there's no other way of saying that, just straight up racist. So way to say thank you. All right, so let's look at faults. We're talking about faults already. If you don't know what a fault is, now you will know what a fault is. But I'm also going to give you some types, and I'm going to expect you to know these for exams. I'm going to expect you to be able to draw me a picture and to understand the way these things move. So a fault is just a fracture. It's a crack in the earth, right? But the way we differentiate a fault from just a regular fracture or from a joint, which is a parallel set of fractures, is the fact that movement has taken place. So two halves have moved relative to each other. So if you get my little pen over here, here is the rock, there is a crack, you are this little guy right here, there you are, you're this little guy, and your head has come off apparently. Okay, your head is detached. Okay, now it's attached. You kind of have eyes actually, it's a bit creepy looking. Okay, so that's just a fracture at this point. If movement takes place on this thing, so one side moves relative to the other. So say this side now jumps up. So now it's up in the air here, right? That is a fault. So just a fracture with movement. So we've got a bunch of different types of these things. I'm going to unpack those types now. All right, let's look at the different types. So here, for example, is a fault. So where is the fault in this photograph? Well, you can see the fault is, it's right here. It's kind of extending along here. But it extends down that direction. I mean, it's a planar feature which extends down to depth. And you can see movement has happened here. Well, what's happened? I mean, let's get rid of this. It's going to confuse you. This side has moved up relative to this side, and this side has moved down relative to that side. Right? So that's one kind. Now, this side over here might have moved up, and this side over here might have moved down. I mean, that could have been different movement along. We'd actually give that potential thing, which is not what has happened here, we give that a different name. So there's your fault, right? That thing, by the way, that exposed surface, and you don't always get these. If the motion had been this direction, you would not get one of those, right? If it had just been left-right, right? But where one side moves up or down and there's an exposed surface, that is the fault scarp. That's the fault scarp. Okay, so how many faults do you see in this picture? Just take a second and look at how many faults you can see in this picture. You guys done? You counted? I count 3. I'll show you where the 3 are. So I'll show you where the 3 are. There's a fault there, and then there's that fault right there. This is his fashion fault. By the way, in class, that gets a very good laugh. I have no idea if it did at home. In class, my delivery is a little more energetic as well. But yeah, you can see 3. And I'm going to point out something actually to you seriously, though, here, which is that when we want to figure out the direction motion's taken place, we're going to pick a marker bed, usually, is what we'll do. So you see, for example, this black bed there corresponds to this black bed right here. And this bed here is going to correspond probably to this bed down here. This bed here corresponds to this bed right here. And so we can see that this side has moved down relative to this side right there. That's the motion that the thing has gone. So this whole chunk here seems to have fallen down that direction. Also, imagine, I want you to note, because we're talking about this later, imagine you're going to walk down the fault itself. If you're going to walk, you would be walking this way. So there is the fault here. The fault goes like this. That is the fault, and the little guy would walk down there. He would not walk this way. Now, why is that relevant? And why is that relevant? He would not walk that way. So if he was going to walk down here, where is he going to walk? He's going to walk like this. He's going to walk right there. You're saying, Jason, why are you drawing this? Because it's actually really important to classifying it. And you'll see that in a second. So there's the second fault. And again, there's that marker bed. In this case, if you're trying to figure out where the marker bed is over here, I can't see it over here. So I'm not sure which direction it went. My guess would be it's done exactly the same thing. and it's up here. That marker bed's just gone away. It's gone too far and it's been eroded away, I think. But I don't know. I don't know. You don't know either. All right, so there's the relative motion right there. Okay, here is another example. So which direction was the relative motion in this case? Which direction was it in this case? So this is the kind of thing you're going to find if you go to California and you look at the San Andreas Fault. So you can see there hasn't been any up and down motion here. These are, by the way, plants. These are rows of as a crop in someone's field, and that's the actual San Andreas Fault right there. You can see the fault is running right along here, and you can see the motion has been this direction. That is the relative motion. So this is a transform fault or a strike-slip fault. A strike-slip fault. And so that's the way the motion has gone right here. There you go. So there's your strike-slip fault. So that's the first kind. If there is just lateral motion, we're going to call that a strike-slip fault. So the movement is side to side in this case. All right, so there it is. And how might we look for evidence of this? Well, if you fly around, anytime if you fly to California or to Nevada, you go to Las Vegas or something, look for it because you can see these things as you go along. You can often see evidence of a fault in terms of, sometimes you can actually see it, not in this case here, but often where a fault is, right? Because a fault creates a zone of weakness, often the river will actually erode into it. Sometimes you can actually just see them as linear river features. In other cases where it bisects a river, right? This river point here used to connect to there, but the faults literally move them apart and the river has just gotten fed up and is joined back together here. But you can see these kinds of things in the surface. You can see this kind of evidence in the surface. That's the actual San Andreas Fault there, by the way. You can go and literally walk around and jump back and forth on it. Okay. So there are different, if you don't have movement that's just lateral, you have movement that's up and down. We call that a dip-slip fault. The terms strike and dip, I don't care that you learn these, but the terms strike and dip are ways that geologists talk about a planar layer of rock. So let's say imagine this layer, I'm not going to quiz you on this, but let's say you've got this layer of rock here. You see it goes into the ground at some angle, and it also kind of bisects a horizontal at this angle. This is called strike. And the way it goes to the ground is called dip. So a fault that moves down or up is literally moving along dip, and one that just moves laterally is moving along strike. That's where that terminology comes from. It's a mapping term. You don't need to know strike or dip, but it's not just made up terms. They really are a descriptive term using terminology that you're not familiar with. Okay, so we're going to look at two different kinds of dip-slip fault, and there's a subtype. One of those two different kinds has a type A and a type B. So you can see this case, it moves up, and this one moves down. But of course, it could be the other direction. This one might have moved down. And so those are your two types. So we're going to ask, we need a reference point. So if we want to refer to that as opposed to the one below it, right, how do we refer to that versus that so that we can talk about this moving up or that moving down? So we're going to do that by defining one unit, the top one here, as the head wall and the bottom one as the foot wall. And they're easy to remember. Remember my little guy? Here's my little guy again. Here he is. Remember my little guy? My little guy, where's his head and where's his feet? His feet are on the foot wall. There's the foot wall. And his head is on this here, the head wall or the hanging wall, which is hanging over top of him, the hanging wall. So here's your hanging wall, right? Here's your hanging wall. So in each case, we are interested in which one of these things is going to be moving. Right? We're interested in whether the hanging wall, the one over top, is doing moving. So in this case, how's your little guy going to walk? He's going to walk down the hill like this. Here he is. There's your little guy. So where's the foot wall? That's the foot wall because his feet are on it. Where's the hanging wall? That's one there. It's the one that's not the foot wall. And you can see the arrows telling you this one's moving down. So one where the hanging wall moves down is a normal fault. And one way you might imagine this is imagine you're holding these two blocks together and you just let go of one. You know that things in the world tend to move down. Things don't tend to suddenly start floating up in the air. That's just not how the world works with gravity. And if you see that, that's weird. If you see something start going up, it requires force to do it. Whereas things just on their own will go down under gravity. And so where things behave as you expect the world to do, that is the normal way things behave. That's how I like to remember these things, right? Just think about things tend to fall down. So when the hanging wall falls down, that is a normal fault. All right, a reverse fault is surprisingly the reverse of a normal fault. So in a normal fault, the hanging wall would move down. The reverse of that, the hanging wall moves up, and the foot wall then moves down in terms of relative motion. The foot wall might actually be totally constant. We're talking about relative motion, right? The hanging wall is moving up relative to the foot wall. So where you have a reverse fault that is at a very low angle. So, in terms of these faults, we could have a fault that moved like this. So there's our fault, right, where it moves this direction. Right, there's your hanging wall. And you can see the angle here is what? I don't know, like 75 degrees, 80 degrees. In this case here, though, this angle is very low. If you actually wanted to measure this angle here, it's very low if you measure that angle in there. And so anything which is less than 45 degrees, so something which is less than, approximately, how do I do this here? Something which is lower than approximately that. So an angle less than that is going to be a thrust fault. And a thrust fault is just a reverse fault. It's a type of reverse fault, but we're specifically going to refer to it as a thrust fault if the angle is less than that. All right, so take a moment and look at these pictures and tell me, what are you looking at? Are you looking at reverse faults? Are you looking at normal faults? Take a look. Actually, you know what? I'm going to keep talking. Just pause it for a second and then unpause once you know. Okay, I'm going to assume you know you have unpaused it now. Let's just take a look. So first off, here's your little guy. Here he is. So he's walking here. Here he is. I'm going to give him a head. I'm not going to give him heads. It takes too long to draw a head. So that's the hanging wall. That's all we're interested in. Here's your little guy. We did him before. Here he is. There he is. Again, he's going to be headless. Actually, it's too weird. I got to give him a head. It takes time, but I'm going to give him a head. Okay. So there's your hanging wall. In this case, the hanging wall is moving down. So that is a normal fault. In this case, the hanging wall is moving up. And so that is a reverse fault. Easy peasy. And particularly, remember, this is a thrust fault because it's low angle. So it's a Kuiper reverse fault. There's your normal fault. So how do you make something jump up? Remember, things are just going to fall down under gravity. So imagine that you're just looking at this and you're an engineer and you say, I want to make this go on top. How are you going to do it? How are you going to do it? Well, the answer is going to be pretty simple. You're just going to push this direction. You're going to push that direction. If you do that, this is going to jump up on top. Okay? So in that case, you have to compress it. That's how you're going to make something jump up on top. On the other hand, if you want to make something fall down, you have to move them apart, right? Because this is a whole thing here of lands. You got to pull them apart. You're going to pull them apart. And now think about our boundaries. Remember our boundaries? Right? We have boundaries where things are subducting underneath each other and they are coming together. These are convergent boundaries. And then we have boundaries where things are moving apart. All right? Remember, these are very bad drawings, but remember that we have these divergent boundaries. So where are you going to find one of these guys where they're falling down, a normal fault? How about a divergent boundary? Where are you going to find compression? How about a convergent boundary? Fantastic. Okay. So these are a fancy word, by the way, when things move apart or they're pulled or stretched as extension. So this is an extensional force. This is compressional force up here. All right, here's another kind of fault. We didn't actually know these existed until fairly recently. A blind fault is a fault that can't see you. That's not true. A blind fault is a fault that we cannot see. Right? So a blind fault is a fault which does not extend to the surface. And these are actually super dangerous because traditionally we didn't plan for them because we couldn't see them. If you could see a fault right here, then you know it's a bad idea to build that house right there. That's a super duper bad idea. Right? But if you can't see it here, we go ahead and we've built these. We've done this all over the place where there's actually underlying faults, right? But we cannot see them on the surface. And we've come up with new techniques that allow us to measure micro movements on the surface or to measure even stresses in the surface, the subsurface, that allow us to figure out these things. But now we're realizing that our zoning in some cases in earthquake-prone areas was not as relevant or relative to the risk as we thought because of these blind faults that occur. Okay, so let's get back now that we have some terminology to how we can actually generate energy and force here. Now remember that with plate tectonics, we have movement which is taking place, and that movement is being fundamentally driven by convection cells moving heat up. And so remember that where we've got our plate tectonics, we've got our plate, and that's a really extreme. I don't know why that plate's dipping like that, but anyways, there's your subduction zone, and remember this guy, right, is sinking under its own gravity over here. And that is your slab pull, and then over here you've got an area that is, I can't draw. That's the edge of the screen. I'll just draw it over here. There you go. You've got this area here where they are moving apart, And remember, this is sitting up a little bit higher, and so it's literally just sliding downhill. And that's your really terribly named ridge push. So that's ultimately the force, right? Is that this guy is pushing apart or pushing onto something, right? Because there's something over here. If this slab is getting pushed that direction, right, these guys are interacting together. There's compression taking place right here. Where these guys are moving apart, remember that on the underlying area, you've got a detachment between the lithosphere and the underlying asthenosphere. They're going to be interacting together, but also you're just stretching this whole unit. This whole thing is being stretched, and this area can fail, right? It can brittly just break and move, and you can get movement going on. Also remember that if you're moving these things either together or apart, that means you also have to have lateral movement. You have to have lateral movement. There's a little guy standing right here just looking at it. Lateral. In any case, you've got things moving relative to each other. Except these things don't want to move relative to each other. Right? This is not a slip and slide. This is not an oiled surface. Right? This is rough rock taking place in areas of thousands of square kilometers, tens of thousands, hundreds of thousands of square kilometers sometimes. So there is going to be a massive amount of frictional resistance. Right? Everywhere these things are in contact, they are going to be frictionally resisting it. And this area is going to resist moving. Now, the movement doesn't stop, right? I mean, this is still pushing. This is pushing at it, and this is still pulling at it right here. But if this area stops moving, what is going to happen is that energy is going to be stored within the rocks themselves, or within these rocks themselves. It's going to be stored by stretching or compressing the rocks, right? It's going to start building it up. It's going to start storing it in an elastic way. If you want to imagine this, you can take one of your fingers and start to bend that finger backwards. Right? If you want to do it really dangerously, you can put your face against your hand against your face with your middle finger over your nose, and then pull your middle finger away from your face. And as far as you start pulling it away, you can feel all of that tension building up. And if you release that, it's going to flick back and hit you in the nose. That's a hilarious joke you can play on people. Have them do that and let it go. So all of that stored energy that could go flicking back at your nose, that stored energy is the stored energy of an earthquake. So this is actually a tool that we use. This is a real tool we use in geological engineering. Right, here is a rock sample, and that rock sample, we put it in there and we compress it. And we see what happens to that rock sample. And so in this case, this is probably granite. You can see these little things, but it could be sandstone. I don't know. It doesn't matter. So we want to know when we compress it, what's going to happen. And you can guess that at some point, this rock sample is going to break. It's just going to smash and it's going to break into fragments everywhere. But before it does that, it actually is going to start deforming. It's going to elastically bend. Turns out everything bends. And everything will actually deform up to a point. Now, even glass, you can get glass and put pressure on it. The glass will deform just a little bit, and then it shatters. Something like a piece of rubber or a piece of chewing gum is obviously going to deform a lot. Right? It's really hard to make something like that shatter. If you freeze it, then you can make it shatter quite easily. But all materials will behave in two different ways. One, they will start to deform in an elastic or a ductile way. They will start to bend, and they are going to be storing energy within them. Like all of that bendy energy, it wants to get released, either by flipping and going back to its original position, or by breaking and releasing that energy. And so we can put them in these kinds of machines, and we can measure exactly how they behave. Right? In this case, can I get an eraser? Is there an eraser in here? There's not an eraser. Just see through this. Rocks initially respond elastically. They deform, storing potential energy, which can then be released. And so if you put enough energy on here, what's going to happen to them? Eventually, it's going to shatter, and it's now going to release all of that stored energy. Now, that's one way things can do it. The other way they can do it, actually, is some substances, if you keep pushing on it, they will start to deform a little bit in a way that's elastic, so that if you release it, it goes back to its original shape. But if you keep pushing on it, eventually it's just going to bend, and it'll be stuck in that bent position forever. So think, for example, like a piece of like a coat hanger. Imagine you've got a metal coat hanger or a thin piece of metal of some kind. If you bend it just a little bit and let go, it'll go back to its original position. If you bend it hard, you're not going to have a U-shaped piece of metal. If you let go of it, it's going to stay being a U-shape. That's an example of ductile failure, where it changes shape and it retains that shape after the fact. That's not what we're interested in, though. What we're really interested in is either brittle failure, but more importantly, actually elastic failure. And I'm going to show you that in a moment. So here is brittle failure. You put enough energy on this, and this thing just snaps, it breaks, and it's going to move and release catastrophically all that energy. So that's not the most important thing that's happening along faults, although it is one way. We can brittly fail things and we can release energy like that. That's not the main way that these things are releasing energy. Rather, what's happening is as they are moving relative to each other, right? So here, this thing, you're going to have movement that's taking place, say like this. I think that's the direction it's happening, right? All along this fault, all along here, right? These guys are frictionally interacting and it's resisting the movement, even though it's pushing along. And so what's going to happen is along the edge, it's going to catch and it's going to start deforming the rock adjacent to it. It's going to start deforming because this part is not moving. Everything else is going to start deforming. And all that deformation is stored energy. So in this case here, it's moving along, but this area in between is still not moved. So all of this deformation, that's stored energy that can get released. And it could get released by a new fracture starting in this rock and this part just jumping forwards. But more often what happens is just it overcomes that frictional resistance. And the whole one side just jumps forwards and the other side jumps that way. But they're going to jump and scratch against each other as they jump. So they're going to literally roughly scratch against each other. So if you want, in class, what I usually do is I usually get a table and I push on the table. And if you start slowly pushing on it, you can do this in your kitchen. You can do this right now at your desk. If you're at a desk, if you're at a computer, just push your computer a little bit. And you can start pushing a little bit. What you're going to see is your fingers or your hands. And the first part, the thing doesn't move. You just slowly apply pressure. But your hands are going to start actually deforming. Right? They're going to start storing it by bending your fingers or bending your arms. And as you keep putting on energy, eventually whatever you're pushing is going to jump forwards. And if it's something like a table, it's going to make a noise. It's going to go as it moves forwards. That noise, those are literally P waves. It's a kind of seismic energy being released at you. If you push it enough, you could actually feel the vibrations of that coming forwards, but you can certainly hear the vibrations. So that stored energy, which was in your hands or in your arms, as you were pushing it, it wasn't moving. That suddenly gets released, and it gets released forwards, and it manifests in the form of sound waves, of shock waves moving along. So there it is, it ruptures, it moves forwards, and it releases that energy. Now at that point, the system hasn't stopped moving. It's just jumped forwards a bit. But overall, the entire plate is still moving relative to the other plate. And so energy is going to start accumulating again. Because now that the energy has been released, which was able to overcome that friction, it's gone back into its frictional resistance stage. And so it's going to start building that up, deforming the rock again, and that's going to repeat and repeat and repeat. And the interval of time between each release is going to be dependent on the nature of the fault, the amount of stored energy, the rate that they're moving, all of these sorts of things, right? Whether other smaller faults or help relieve that energy. So each system is complex, but the actual underlying part is really simple. Two rocks are moving relative to each other, propelled by tectonic forces. They get stuck together by friction. Because they cannot move at the area they were stuck, all the rocks around them start to bend and store energy elastically. Eventually, that stored energy, gets so big that it overcomes the friction. The rock jumps forwards, scraping past itself and causing vibrations. And those vibrations are earthquakes. That's all they are. They're just the vibrations formed when these two rough rocks move past each other. Now, let's go back to that idea of moment, what it is. So how big is the vibration going to be? Well, it depends on, if you want to think back to the desk example, the further you push the desk along the ground, the louder the noise and the longer it's going to go. If it was a big desk versus a little desk, right, it's going to be louder still. If 10 people all push desks at the same time, it's going to be a lot louder than one person doing it. So you remember, it's the surface area, the total area that moves, the distance it moves, and then the rocks themselves. How rigid are they? Right? That's what's producing the total amount of energy. In our analogy, it would be the amount of sound, right? But in a seismic system, it's a whole set of different destructive waves that come out. So that is the end of the lecture for today. So in review, the big take-homes I want for you are, one, to understand the way that we measure them, both the instruments we use, so a seismometer or a seismograph, what we are measuring, which is movement on the ground, right? Directly movement on the ground, what we are using those measurements for, which is to estimate moment, or the actual amount of energy released somewhere deep in the ground that we can't directly access. What moment is. Moment, remember, is a function, it's the energy release. It's a function of the area of slippage, the distance that those rocks moved, and the rigidity of the rocks, the type of the rocks themselves. I want you to know the difference between the moment scale, the moment magnitude scale, and the Mercalli scale. So magnitude versus intensity. One's a measure, remember, of actual on-the-ground effects of damage, how it affected human beings, and one is a estimate of the amount of energy released at source. I want you to remember the different types of faults: normal, reverse, transform, and thrust faults. I want you to know, and this is the fundamental one, and again, I promise you that this is going to be on the coming midterm as well as the final exam. I want you to be able to explain to me how the elastic rebound theory explains how earthquakes move. And so this is just this idea that faults get stuck together, and I'm going to give you a term next class for the faults getting stuck together, and they move relative to each other. You know, the ground around them is moving relative to each other. Where they get stuck, everything adjacent to it deforms to accommodate that motion that cannot move along the stuck area. The word for that, by the way, is an asperity. I'll talk about that later on. That's an area along a fault that gets stuck. It doesn't have to be the whole fault, one little area of it. And then eventually the pressure gets enough, it overcomes that frictional resistance. It jumps forwards, the rocks scrape past each other, releasing seismic energy. So that's it. That's the big take home out of today's lecture. So I'm going to go now and climb some volcanoes. One of the things I'm doing now after I've just finished up a bunch of talks, really interesting talks, a lot of them on disaster communication. Got some cool things to teach you guys, some cool things I learned, is now to go and actually take a look at some volcanoes. I'm going to take some photographs we'll be talking about, and I'm going to bring some samples back, hopefully, to show you some pretty recent volcanoes that have occurred in the area in the last few thousands to few tens of thousands of years. All right, so I hope you guys are doing good. I will post the next lecture probably tomorrow, really. I'm going to try to, if I have some time to do it tonight, but it'll probably be tomorrow. If you have any questions, please do email me. You can email me if you want to talk about things in detail. Send me an email, and we will set up a chat time over the internet. I can also be reached by my regular text number. It's on the syllabus, but it's 902-224-5506, 902-224-5506. You can text me if you have any questions. There is going to be another quiz going up this Friday that will be on until Tuesday. Remember to take it. It's going to include all the earthquake stuff. All right, hope you guys are having a good week, and I hope you found this way of learning conducive to your learning. All right, bye.